Okay, good morning, everyone. So last time we had been talking about the eigenvalue problem for orbital angular momentum. And so we were interested in constructing the following things. So let's say we want the wave function in spherical coordinates. So I'm writing a bra r theta phi for the eigenstates of angular momentum, that's L and M, and any other quantum number that there might be. So this n is sometimes called a radial quantum number. And this is a wave function labeled by the values of n, L, and m. And it's a function of r, theta, and phi. And our strategy is divide and conquer. So we split this up into a radial function of r only, and then a function of theta and phi only, which depends on L and M. Okay, so this, in a way, this defines what we mean by the radial wave function. And the idea is we're going to just work on the YLMs, and then for some specific physical problem, we'll have to worry about what the functions of R are. What we'd found last time is just what happens when m equals L, which is the largest possible value it can be. And what we found was that YLL theta phi is an arbitrary phase factor, which is -1 to the L power. That's for later convenience. And then an incredibly ugly normalization factor, which turned out to be this, or turns out to be this, 2L plus 1 factorial over 4 pi under the square root, and then a factor of 1 over 2 to the Lth power times L factorial, and then a factor of sine theta to the Lth power times e to the I L times phi. Okay, so all of this is normalization factor. And really what we worked out last time by solving a differential equation is this dependence on theta and phi. Okay, so the normalization, the way that works is that we're requiring that when we integrate over all positions, so we're doing an integral 0 to infinity, and there's an r squared dr, and 0 to 2 pi d phi, and 0 to pi sine theta d theta. And then we're multiplying by the square of the wave function. That's supposed to equal 1. Okay, and in doing this, in order to define this normalization, we're assuming that for the radial part, it's normalized in the following way, that if we integrate over all r of r squared times the magnitude of Rn, that's supposed to equal 1. So later on, when we apply this to some specific problem, some specific potential, we'll have to make sure that we accomplish this goal if we want things to be normalized. We're also using this fact, this is not an assumption, this is just a true fact, that if I integrate from 0 to 2 pi of the phi dependence, okay, this is just integrating 1, so I forgot my d phi there, that's equal to 2 pi. And so really the hard part is coming about when we integrate sine theta to the L squared. And so that's going to give a factor of 0 to pi. Sine theta d theta is otherwise known as d cosine theta of sine theta to the 2L power. And that's a doable integral, and that's where the ugliness comes from. So it turns out to be 2 to the 2L plus 1 times L factorial squared over 2L plus 1 quantity factorial. That's the result of doing that integral. And so if you plug all that information in, that's where this normalization factor comes about. Okay, so that's why that occurs. And now that was all for m equals L. And now we have to worry about every other possible value of m. But that we can do pretty easily, at least mechanically. It's still a little bit ugly arithmetic. But for all other m's, namely L minus 1, L minus 2, etc., until we get down to the lowest value, which is minus L, all we have to do is apply the operator L minus, the lowering operator, because we know from our general treatment of angular momentum how it acts. And that is, for example, if we act with L minus on the state LL, that means the state with m equals L. Then there was this formula that had an h bar and then a square root of L times L plus 1 minus L times L minus 1, we're plugging in for m, times the state with m lowered by 1 unit. And that simplifies to just h bar square root of 2L times L minus 1. So what that means is, if we now plug that in to our formula above, that means the wave function psi n L L minus 1 as a function of r, theta, and phi is 1 over h bar square root of 2L. Okay, and now we need to put in what we worked out last time. I'm leaving a big box here for that. What's going to go in the box is going to be the differential expression for L minus as a differential operator. And this is acting on psi n L L of r, theta, and phi. Okay, this is known. And what goes in the box is minus h bar e to the minus I phi partial theta minus I cosine theta over sine theta, partial with respect to phi. That was the differential operator form of L minus. So it's a little bit of a mess, but the nice thing is, if we look at it, we notice that it doesn't affect the radial coordinate r at all. It doesn't act on the radial coordinate. So this doesn't affect capital R, that function. And so this whole thing is just going to be the same radial function times L minus 1 of theta and phi. Okay, and so now by comparing the known stuff here, we just have to take some derivatives, we're going to get the wave function with m equals L minus 1. Okay, and in particular, this is true where L minus 1 as a function of theta and phi is minus e to the minus I phi over square root of 2L. Notice the h bars cancel. Okay, and then we have to take a derivative with respect to theta plus L times cosine theta over sine theta. times the original YLL. So one thing that happened here is we took the derivative with respect to phi, and then we noticed that that's easy to do because back up here, it's acting on e to the IL phi, and there's no other phi dependence. So that's just turning this, once we include this minus I factor, that's just turning it into L. And so everything is just a differential operator with respect to theta. Another interesting thing about this is, or useful thing about this, is notice that this is proportional to e to the I phi times L minus 1. So we already know how this thing depends on phi without doing any work. And the reason it's that is this is e to the I L phi, and this is e to the minus I phi. And that's why they combine to give this factor. Okay, and so you can compute this, but I won't, because instead I'm going to write down the general thing that you get by doing this over and over again for any m. So if you keep doing this, however many times you need to get a general m, you find YLM theta phi is a rather messy expression. So first of all, there's a minus 1 to the L factor, and that comes about just because we already made a decision to include that factor in YLL, and it just stays there as we keep acting with the other factors. There's also a factor of square root of 2L plus 1 factorial over 4 pi. There's a factor of 1 over 2 to the L times L factorial. So all of this is coming, again, from our normalization factor here. But then there are other normalization factors that come from operating with this differential operator, which is L minus. And they turn out to be the following. Square root of L plus m factorial over 2L factorial times L minus m factorial. Okay, and now there's e to the I m phi. That comes about because we started with e to the IL phi, and then we just kept lowering it, and every time we lower it, every time we lower the value of m, we're getting a negative e to the minus I phi, so that turns that into this. Okay, and then there is a sine theta to the minus m times this many derivatives of cosine theta, namely L minus m of them, times sine theta to the 2L power. Okay, so it's a quite messy expression, but if you've got a computer that's good at taking derivatives, it's no problem. So it divides up into various parts. This part, the really ugly part, is the theta dependence. Okay, the phi dependence here is relatively simple. It's just e to the I m phi. And it's the only complex part of this. Everything else in the expression is real. Then there's this ugly part here, which is normalization. And then there's the minus 1 to the L part, which was an arbitrary phase convention. And this is the thing that depends on what book you're reading. Actually, the normalization factor here also depends on what books you're reading. mostly, for example, if you're reading a book on optics, they'll talk about the same YLMs, but that's not in quantum mechanics. So they don't have any obligation to normalize this the same way that we do in quantum mechanics. And so they'll often treat this normalization factor in a different way. They'll just define it differently. Okay, but even in quantum mechanics books, this first phase factor will differ. Okay, and the normalization factor here is fixed by this requirement that if I do an integral over phi and an integral over theta, and then I do y L prime m prime of theta phi, and I complex conjugate it, and then I do y L m of theta and phi. That's one if and only if L and L prime are the same and M prime are the same. So I have Kronecker deltas there. Okay, the reason for this is, let's look at this factor. First of all, this we can rewrite. It's often convenient to rewrite this as integral minus 1 to 1 d cosine theta. And as just a nice way of writing it, because these integrals appear very often in different situations, this is often written as just d omega. So d omega is a synonym for an integral over phi and theta over all possible values. So we'll be using that as a shortcut notation going forward. And so basically what this statement means is easier to say in Bra-Ket language. In Bra-Ket language, this is equivalent to the statement that if I take the inner product of two angular momentum eigenstates, it's one if and only if they're the same state. They're the same eigenstate. Okay, and where does the theta and phi come in? That comes in from completeness. Because it's equivalent to saying that we're going to insert a complete set of states and integrate over all of them. So I do integral d omega L prime m prime theta phi Lm. Again, that's the same Kronecker delta. So I've inserted a complete set of position eigenstates. I haven't written the R part because the radial part is normalized to 1 and doesn't do anything. And so that's the statement of what this equation actually means. Okay, we start with orthonormality, we do completeness, and that gives this. Okay, other statements we can make are we can talk about the hermiticity of L sub z. So note, first of all, that L sub z as a differential operator acting on YLM is equal to minus I h bar times I times m YLM. That's just because the L sub z contains a derivative with respect to phi. This part right here has an e to the I m phi, so that turns that into I times m. Okay, and then minus I times I is 1. So this is h bar m YLM. For some unknown reason, I've flipped these and I should not have. Okay, and that's verifying what we know the eigenvalue with respect to L sub z was for this eigenstate. Okay, and then if we look at hermiticity of L sub z, that says, okay, if I integrate over all omega and I do psi 1 theta phi star, L sub z acting on psi 2 theta phi. Okay, this L sub z here is interpreted as, again, the differential operator. That this is supposed to be equal to the complex conjugate. So I'm writing a big complex conjugate box of integral d omega psi 2 theta phi star L sub z psi 1 theta and phi. Okay, which you can check to be true given the definitions that we've already made. So notice when you take the complex conjugate, really, because it only involves a factor of e to the im phi, you're just changing e to the im phi into e to the minus im phi for each one of these expressions. Okay, so completeness, we can rewrite the statement of completeness again. Now I'm going to include the R part. This is completeness in spherical harmonic language. Okay, and so we start with some wave function, as we did at the beginning of class. But now I'm not assuming necessarily that this is an eigenstate of angular momentum. I'm just letting it be an arbitrary psi. So this is a wave function psi of r theta and phi. This is going to be a sum over all L's. And we know they can be any non-negative integer, and a sum over all m's, which go from minus L to L. And then there's theta phi Lm times the radial part, tensor product with Lm, all of that acting on psi. Okay, so I've inserted a complete set of states. These things right here are what we define to be the spherical harmonics. And now let's think about what this object is. So this object is something that depends on the state, and it depends on R, because if I change R, it will change, and it depends on L and M. So in other words, it's some set of coefficients that I can write like the following. I can label it by L and M, and it depends on R. Okay, notice it does not depend on theta and phi. There's no theta and phi in this. The theta and phi part has been moved entirely into this part, which is the spherical harmonics. Okay, and so that's a useful way of expanding any function. Notice I didn't assume this was an eigenstate of anything in particular. It doesn't have to be. So we're saying that any underlined function can be written as a linear combination of spherical harmonics with coefficients that depend on R. So with R dependent coefficients. Those are the CLMs. So if we're armed with that knowledge, then it becomes a useful exercise or a useful thing to do to be able to figure out what the CLMs are. And so that's an important problem. to find these coefficients, what we do is we multiply both sides of that equation by a spherical harmonic complex conjugated. So I'm going to choose it to have indices L prime and M prime. So because they're going to be arbitrary and I don't want to confuse them with this M and this L. Okay, and so this is a function of theta and phi, and I'm choosing to multiply by the complex conjugate. Since I'm multiplying both sides, I'm allowed to do that. You can't stop me. And then I can integrate both sides. Okay, and so what do we get? We get integral d omega y L prime M prime theta phi star times my arbitrary function that I'm trying to express as a linear combination of spherical harmonics. And we say this is equal to, from the other side of that equation, sum over all L's, sum over all M's, times my CLM coefficients that we're trying to discover. And then what appears is, again, I have to integrate over all omega. Since I did so on the left side, I need to include my y L prime M prime, since I put that on the left side. And then I have YLM. Okay, but now's the good part. The good part is this was defined, the way we defined everything, to be a Kronecker delta. So that means even though I'm summing over all L's and M's, the only ones that actually contribute in the sum here is when M equals M prime and L equals L prime. So that means I can do the sum by taking it away and just plugging in those values. So this is equal to C L prime M prime as a function of R. Okay, only one term in the sum survives. In fact, it's a double sum. All right, now having done that, we can just to be neat, we can rename what we originally called L prime as L, and what we originally called M prime as M. And so we get the following equation that's very important. Psi of R theta and phi is equal to sum over all L's, sum over all M's. These coefficients, CLMR of YLM theta and phi. So what that equation's telling you is that you can write everything in the spherical harmonic basis, where the other part of it is the CLMs are known because they're just the integral over all theta and phi times YLM theta and phi star psi R theta and phi. So these equations go together, right? And it says, if I give you a function, any function, psi of R theta and phi, you can plug it into this integral, do the integral somehow. That'll give you the coefficients. And then the coefficients are telling you how to write that function in terms of spherical harmonics as a linear combination. Okay, so I want to emphasize these equations are true for any wave function. Psi, or any ket, in fact, psi. So the wave function, of course, corresponds to some ket. What I mean by any here is in particular that we do not need this to be a system where the Hamiltonian or anything else is invariant under rotations. So don't need spheric symmetry under rotations for the Hamiltonian. Now it's usually, or I shouldn't say usually, but it's very often the case that this will be particularly useful if my Hamiltonian is invariant under symmetry of rotations. But it's important to recognize it's not necessary. If you just want to write things in terms of spherical harmonics, you can always do it. So one case where that's going to be important is a situation where we're mostly invariant under rotations. And what that means is there's an important part of the Hamiltonian that is invariant under rotations, and then maybe there will be a little bit that's not. And so we can treat it in terms of spherical harmonics and then isolate the part that's not invariant under rotations and somehow treat it separately. We'll do that later using what's called perturbation theory in physics 661. Okay, but in any case, suppose you've done this for any wave function. Now you can ask questions like, what's the probability of measuring angular momentum? So in particular, I could measure L squared, which could give me these possible values. And I could measure simultaneously or compatibly, I could measure L sub z, which gives me h bar times an integer. Okay, these commute, so they're compatible. So I can, if I want, measure one of them or both of them at the same time. And the probability of getting any particular result, L and M, is given by, probability L and M is given by the following. So I have to sum over all states, r squared dr, of r cross Lm, that thing acting on psi, squared. So this is really just the postulates of quantum mechanics in action. It says we sum the square of the wave function over all possible values compatible with the result of the measurement that you got, which was L and M. Okay, so just to label these things, these are the eigenstates of L squared and Lz that you're measuring. The R here is a degeneracy label. And remember, when you do this in the postulates of quantum mechanics, it tells you you're supposed to sum over the degeneracy labels after you square. So this is my sum over degeneracy labels. And when we wrote the postulates of quantum mechanics, we called them rho, but that was just a generic label, and now we're being specific and we're calling it R. Okay, but now we can simplify this because we can say, okay, this equation up here told us what that integral is. So the PLM is integral over all R times the CLMs, which are functions of R, squared. Okay, so that's one reason why you'd want to know what the CLMs are. You have some arbitrary wave function up here. You can write it in terms of the CLMs, and then the CLMs tell you what probability that you get for measuring the angular momentum, L squared or L sub z, and getting some particular values. You just need to know the coefficient for those particular values, and then you need to do the integral. Of course, doing integral might be easier or harder, but that's the strategy. So that's if you're measuring both of them at the same time. And of course, you could say, well, let me just measure one of them. So let's say I just decide to measure L squared. So then the probability of getting L is gotten by now I treat M as a redundancy label for M, and I just sum over all M's of the PLMs. Okay, so this is the probability of measuring L squared and getting the result H bar squared L times L plus 1. Okay, or I could measure just L sub z, and then I would treat L as the redundancy label. And so I'd do a sum over L of PLM. So this is the probability of measuring L sub z and getting the result H bar times M. Okay, or I could measure them both and add up all the possibilities. And then I should get 1. So if I write 1, I can write that as the sum over all possible L's and M's that I could have gotten times their probabilities, right? And that's equal to just plugging in the individual probabilities again, r squared dr. Here's my sum over all L's. I need to go to infinity. Then I go from m equals minus L to L of CLMR squared. And so that's just expressing the fact that if I sum over all the possible probabilities that I could have gotten for any results of the measurement, I have to get 1. Okay, but it's also the normalization condition for these coefficients. All right, questions on that so far? No? Okay. So we had this general formula way back up here somewhere. We had this sort of horrible formula for YLMs in general. But in many, many problems, what you need is just the lowest few, meaning the values with L and M that aren't too large. And so it's a good idea to see what those look like. Okay, so this is the lowest few. As we'll see later in physical problems, it turns out that states with lower energy, which are the more important ones, because you end up there more often, are the ones that tend to have also L not too large. And if L is not too large, then M can't be too large either. So that's the motivation for this. So Y00 is the easiest one, because that doesn't depend on theta and phi at all. And so the normalization just sets it equal to 1 over the square root of 4 pi. So it's a constant. And then there's Y1. And if M is plus or minus 1, it's nice to treat them at the same time. This turns out to be minus over plus square root 3 over 8 pi sine theta e to the plus or minus I phi. So again, by knowing what M is, you automatically know what the M dependence is. It's just the exponential of I M phi. Okay, and then a useful thing to notice about this is this thing is largest for theta equals pi over 2, which is in the equatorial plane. Okay, whereas the state Y10, theta and phi, is the normalization factor is square root of 3 over 4 pi. The theta dependence is cosine theta, and we know it has no phi dependence. We read that off immediately from the fact that M equals 0. Okay, and then for y2, when L equals 2, the possible values of m are plus or minus 2, first of all. This turns out to be the unlikely looking number square root of 15 over 32 pi. Sine squared theta. And then again from the m, we read off immediately what the phi dependence is. For psi 2 plus or minus 1. This is minus over plus square root of 15 over 8 pi. Sine theta, cosine theta. And again, the phi dependence is the easy part. And then finally, psi 2, 0, theta and phi is square root of 5 over 16 pi. 3 cosine squared theta minus 1. You just get that by doing the theta derivatives. And of course, it has no phi dependence. Okay, and then you can look these up in tables. There are books that have tables of them. If you do in Mathematica, Mathematica knows these things. I think in Mathematica, it actually even in Wolfram, it actually uses the same convention that we're using in this class, but I won't swear to that, so don't trust me on that necessarily. Okay, but another fact is in our convention, specifically our convention for the phases of these things, YL minus M, theta and phi, is equal to minus 1 to the m times the complex conjugate YLM theta and phi star. So again, just thinking about the phi dependence of this, that part's obvious because this YLM is like e to the im phi. The complex conjugate turns it into e to the minus im phi. And we also know this has y to the e to the minus im phi. So both sides of this equation are proportional to e to the minus im phi. But then the tricky part is this, the way the conventions work, there's also a minus 1 to the m factor. That's maybe not so obvious. And in other conventions, it'll be different. Okay, so all of this could have been done in a different way, or there's a different way of writing it. So for completeness, I should tell you what that is. So another way of writing. And depending on, again, if you look at other books, sometimes they'll start with this way of writing it and then talk about the way that I've done it up till now later. But whichever order you work in, if you look at the YLM, theta and phi, you can write it like this. So the normalization factor is going to look different, but of course, secretly it's the same. We're isolating out L minus m factorial and L plus m factorial in a square root. There's a minus 1 to the m factor. There's an e to the im phi factor. And then everything else we write as PLM, which is a function of cosine theta. Well, really, it's just a function of theta, but of course, any function of theta you can write as a function of cosine theta. And these things are known as associated Legendre functions. Many books call them associated Legendre polynomials, which I'm going to put in quotes because they're not polynomials. So they're actually only polynomials if m happens to be even. But for some reason, they got named polynomials early on. And so many, many books will call them polynomials. Okay, so what are those things? They're the solution to a differential equation. PLM, instead of cosine theta, I'm just going to write it as U. This is the solution to what turns out to be the eigenvalue problem in differential form, namely d by du acting on 1 minus u squared d by du of our function, PLM, plus L times L plus 1 minus m squared over 1 minus u squared, multiplying our function. So the first part of this expression is a differential operator. The second is sort of the eigenvalues coming in, that this is all 0. Okay, so this turns out to be equivalent. It's the same eigenvalue problem, just written in a different way. So in particular, for m equals 0, then PL0 of u is often just written as PL of u without the superscript. That really is a polynomial. Those are the Legendre polynomials. Okay, and they satisfy a simpler differential equation. Just for the record, we can write it like this: 1 minus u squared second derivative minus 2u first derivative. All of that is coming about from this part right here. Okay, plus L times L plus 1, and of course m is 0, so I don't have to write the last part. That acting on PLU is equal to 0. Okay, for large L and M, it's interesting to look at what happens. Then YLM, theta and phi, is proportional to sine theta to the nth power, which is largest for theta is approximately pi over 2. That's a general statement that generalizes what we said before for the case of L equals 1. So if we have some xy plane here, and so this is the z and this is the x, for example, then when L is very large, basically what's happening is we're saying the wave function is such that it's going to be very large along the equatorial plane and not so large up here, which is sort of corresponding to what we might imagine for a classical system that's spinning very rapidly. All right, we're out of time today, and I've been going over lately, so today I'll not go over, but next time we'll talk about the parity properties of these, which is what you get when you take r, the coordinate, and replace it by minus itself. So these things turn out to be eigenstates of parity as well as angular momentum. They're eigenstates of both. Okay, and then we'll do some examples of how to use these things for real problems. All right, so that's going to be it for today. I wanted to remind you that homework 8 is due tomorrow at midnight, not today. And you should turn it in on time because on Friday morning, probably right after class, I'll be emailing you the solution. So you'll have them to study for midterm 2. Midterm 2 is on Monday. On the course webpage, I've posted a set of some information for midterm 2, but basically, other than the content, it will work almost exactly like midterm 1. It's in the same room, same amount of time. It'll probably be 2 problems. You should be familiar with how to apply the postulates of quantum mechanics in any situation in this class. But for this particular exam, it's going to be very, very heavily oriented towards harmonic oscillator in all of its aspects. That means you should be familiar with the harmonic oscillator in 1 dimension, the cases that we've looked at in 2 and 3 dimensions for homework and in class, the coherent states, just anything and everything having to do with a harmonic oscillator is what this exam will cover. Okay, are there any questions?
Professor, so can we bring 2 pages again?
Yes, so everything else is exactly the same. And again, you can, if you have questions, you can look at the information posted on the course webpage. But again, it's exactly the same format and everything as the first midterm.
And will the material that was covered in the first midterm also be in this midterm?
That's where my statement that it's very, very heavily oriented towards the harmonic oscillator comes in. So besides the harmonic oscillator, though, as a general thing, you should know how to apply the postulates of quantum mechanics to any situation. Okay, but it's since the midterm, we've had homework set 6, 7, and 8. And so those are the things that you should very, very strongly work on studying.
And so considering the fact that we already had the 2 pages for the first midterm, like if we want to use those, do you give us like an additional 2 pages for the second midterm, or no, is it just 2 pages?
It's just 2 pages. So my guess is you'll probably want to make a new formula sheet. So yeah.
Okay. And will today's material be on the midterm, and like Monday's material?
No, because it's really, you should think of it as covering the intersection of what's in what we're talking about in class and what was on the homework. So that doesn't mean it's necessarily exactly like what's on the homework, but the concepts that are tested on the homework are going to be the same concepts that will be tested on the midterm. So again, very, very heavily slanted towards the harmonic oscillator. And what we talked about today was not the harmonic oscillator. So, okay. All right, any other questions about the midterm or homework or today's lecture?
I have a quick question about the homework 8, if that's okay.
Yeah, sure.
Okay, so I'm looking at 3D. It's asking if H and LZ are compatible for the Hamiltonian given. And upon doing that, you get a lot of terms that contain 4 ladder operators, AX, AY, all that stuff. It doesn't really seem like no matter how you them, you can't really get any of them to cancel out. This equations like some stuff in line Z and H do commute. Usually it seems when the potential is only dependent on R, but that leads me to believe that this wouldn't be compatible. Am I going the right direction there?
So if you found that the commutator was non-zero, then they would not be compatible. But you should definitely question that, because let's look at this Hamiltonian. This Hamiltonian appears to be invariant under rotations around the z-axis, right? Or yeah. So you should be getting, that's a big clue that you should be getting an answer that's going to say they are compatible.
Okay, that's where I thought it would go. I was having some trouble with the math. Thank you.
Yeah, so if you're getting a bunch of extra terms, something probably went wrong. You should probably look for why they should be canceling.
All right, sounds good. Thank you very much.
Okay. Other questions? All right, so I will, oh, by the way, I thought I'd emailed back to you all homework 6, but apparently I didn't. So I'll be emailing you those and homework 7 probably by the end of today.
Professor, I had another question.
Okay.
Yeah, is there a reason why we only consider J squared and JZ?
I'm sorry, you were breaking up a little there. What was that?
So is there a reason why we only consider J squared and JZ For like we don't consider like, was there a reason we don't consider X and Y?
Yeah, so the reason is because J squared and J sub Z commute with each other. But if we tried to add Jx and Jy to that, they don't commute with J sub Z. And so they would no longer make a complete set of commuting observables. They could never even be part of a complete set of commuting observables. And so that's why we limit it to things that can commute.
So how is it that JZ is compatible, but the other two are not?
So you can choose any one of the three to be compatible. You can choose J sub Z, or J sub X, or J sub Y. And so we've just made an arbitrary choice. It's a traditional choice to choose J sub Z. But once you've made that choice, once you've decided to include J sub Z and J squared, then the others aren't eligible because they don't commute with J sub Z. And so you can't include all of them. So you have to make a choice, and we just chose J sub Z.
It's because like the three axes don't commute with each other, correct?
The three angular momenta don't commute with each other.
Now, is that the same thing for L, or is this just J?
It's the same thing for L because L's and J's have the same commutation relation.
Okay.
Okay.